The final exam will be held through Canvas on next Tuesday, December 1st. For the section 1004, the exam will be from 9 a.m. to 10:30 a.m. And for the section 1005, the exam will be from 11:30 a.m. to 1 p.m. So you get 1 hour and 30 minutes to work on the exam. There will be approximately 25 questions, and most of them are going to be multiple choice questions, and there will be a few short answer or calculated answer type questions. And the exam score will be 200 points, but I will include 1 or 2 extra credit questions in which you can score up to a maximum of 10 bonus points. So the maximum points possible from the exam will be 210. Now this is important. Once you answer a question and you move on to the next question, you will not be able to go back and make changes. So make sure you have definitely chosen the answer that you feel most confident about before moving on. Now some multiple choice questions might have more than one answer. A hint would be that those questions are worth more points, or else you will have a checkbox to select the answers instead of the radio buttons, which only let you choose one answer. So you can realize that this question probably has more than one answer. However, you can't select all the choices. If you do that, I will have to deduct points. You will not receive any points for that question if you answer that way. And also I want to say, like, if there are 2 answers for a multiple choice type question and you get 1 right and 1 wrong, the wrong one is given minus points and it cancels off the 5 points you get for the correct one. So this is like done through the Canvas. So when you finish the exam, the score you see will not be a final score, because I'm going to go through all the exams manually and check for those kind of cases, and I will award back the points for whatever correct answers you got. So once you finish the exam, don't think that's going to be your final score. You might be able to earn more points after I manually check all the answers in your exam. And also when I calculate your final scores, that is like the total score from the whole class that you have at the end, if you are just a few decimal points from the next grade, that is like if you are on a borderline to the upper grade, I will try my best to help push you over to the upper grade. So I will be doing that anyway, so you guys don't have to email me asking if that is possible, because I'm gonna do that anyway. During this 241 lab, we learned several different techniques that are commonly used in organic chemistry experiments, and I decided to categorize them as techniques that we can use to purify compounds versus techniques that we can use to test the purity of the compound. So there is a difference. I decided to show this comparison because some students had a confusion, like when asked for a technique that can test the purity of compounds, some students answered recrystallization. So that is not correct. So we have techniques that we can use to purify compounds from a crude mixture. And we can have solid compounds in a mixture, or liquidized compounds in a mixture. So for solid compounds, we can use recrystallization as a purification technique, or extraction. If we can dissolve these solids in a common organic solvent, then we can do extraction. And there is also solid liquid extractions, which we did not talk about, but that option is also available. Then for liquid mixtures, we can use distillation or extraction in order to purify certain compounds out of a crude mixture. Then we had some techniques that we use to test how pure the final compound is. So we can use gas chromatography if it's a gaseous product or a liquid product, or if we can dissolve the compound that we got in an organic solvent, then we can use gas chromatography to see how pure it is. Or we can use thin layer chromatography, or we can use melting point test, but that would be only for solid compounds. So please make sure you know you are able to distinguish between these different techniques. Go over the labs and see the core concepts for each of these labs. Now in Hickman-Still distillation, we can boil a liquid mixture and separate those liquid components based on their differences in their boiling point. However, you have to remember distillation is successful only when there's at least a 50 or 60 degrees Celsius difference between the boiling points of the liquid compounds in the mixture. So if the boiling points are too close, then you can't achieve a successful separation of those liquid components. So if you get a question, like for example in SN2 lab, the crude product mixture had 1 bromobutane, which was the product we were expecting, and excess reagent, that was 1 butanol. And if you are asked, like, would further distillation help isolate 1 bromobutane from the crude mixture? Well, the answer is going to be no, because here you are given the boiling points and you can see their difference is very small, so they're not going to be able to be separated successfully using distillation. So we will have to use some other technique in order to isolate them from each other. And one more important thing that usually comes up in the exam is where the thermometer bulb should be placed when you do Hickman-Still distillation. So the thermometer bulb should be just below the wedge on the Hickman-Still that collects the distillate. And that is because it will be, when it's at that position, it's correctly measuring the temperature of the hot vapors. So that is why the thermometer bulb placement should be just below the well of the Hickman-Still. After distillation, we did gas chromatography. So this was the technique that we can inject a sample of gas or a liquid mixture into the GC instrument, and it will produce a graph with peaks corresponding to each of the components that was present in the sample that we injected. You will remember that these compounds injected to the GC, they're going to be heated to a high temperature and vaporized and mixed with the mobile phase, which is a carrier gas, and those are neutral gases like helium or nitrogen, and the gas will carry these molecules through a column that contains the stationary phase. Now, there are two characters that would determine the elution order of gas chromatography. So elution order is which peak, which compound will come out first from the end of the column. So you will have 0 minutes here, and you can see the minutes increasing this way. So whatever peaks is closest to the 0 minute, that is the first compound that was eluted. And I want to stress this, that the size of the peak has nothing to do with their boiling points or polarity. The size of the peak is only dependent on how much amount of that particular compound was present in the mixture that we're trying to analyze. So it's solely based on the present composition. Now we talked about when the molecules have no significant difference in polarities, the separation in the GC column is going to be based on boiling point differences. And that's what we observed when we ran a hexane and toluene sample through the GC. And you can see hexane had a lower boiling point compared to toluene. So that means hexane will be mixed in the gaseous phase more than interacting with the stationary phase, and therefore it can travel faster through the column. While toluene has a higher boiling point, that means it's going to spend less time in the gas phase and would mix more with the stationary phase, so it's going to be delayed. Its movement through the column is delayed, so ultimately we see hexane elute first, and then toluene would elute after that. So what if there was a polarity difference between the molecules that we are trying to analyze through the GC? How would we determine which compound will elute first? So we had that kind of example in the SN2 lab, where when we analyzed the crude product mixture, it was a mixture of 1-bromobutane, which was the product, and leftover 1-butanol reactant, and both of these were available in the mixture. And here you have the boiling points given. If you just looked at the boiling points, you would think that 1-butanol should come out of the column first. But since there is a polarity difference, we have to consider that how it would affect their movement through the column. And that is also based on the polarity of the stationary phase. If we had a non-polar column, that means the more non-polar molecule will interact more with the stationary phase, because we learned that like interacts with like. So the non-polar bromobutane would interact more with the stationary phase. Since 1-butanol is relatively polar compared to 1-bromobutane, because it has this OH group, because it's more polar, it's not going to interact that much with the non-polar stationary phase, and it will move faster through the column with the mobile phase. So we would see 1-butanol coming out of the column first, and then 1-bromobutane. However, what if we change the polarity of the stationary phase? What if we use a polar column instead of a non-polar column to separate the same two compounds? Now, relatively, 1-butanol is more polar, and 1-bromobutane is relatively non-polar. Remember, polarity is always relative. Compared to 1-butanol, 1-bromobutane is more non-polar. Now, if we have a polar stationary phase, that means one butanol would be interacting more with the stationary phase, while one bromobutane would not like to interact with the polar stationary phase, so it will move faster through the column with the carrier gas, and butanol would be delayed. So we would see one bromobutane being eluted first and one butanol eluted second in this case. We learned about recrystallization as a technique that we can use to purify impure solid organic samples. So when we obtain our final product from an organic reaction, it will not be pure, it will be mixed with other side products or leftover reactants and such. So if it's a solid sample, we could use recrystallization using an appropriate recrystallization solvent. So we learned that a good recrystallization solvent should have a low solubility for this particular compound at lower temperatures or room temperature, but it should have a high solubility for the same compound when we heat that solvent to a higher temperature. So we need to see this steep curve for a good recrystallization solvent. Now, if you are asked the question, what is a good recrystallization solvent? I've seen some students write ethanol. That is not correct because you are asked to describe what a good recrystallization solvent is. Ethanol might have been good for the compound that we tested in the lab, but that's not the context the question is asking for. So remember that, and remember that poor solvents, either they have not much difference even if you increase the temperature, or they are always soluble, have a high solubility in that solvent regardless of the temperature change. Now, this was the image we had in the lecture. So the green is the organic compound we need to purify, and red is the impurity trapped in the solids. So we put the impure solid into our recrystallization solvent. You can see it's insoluble at room temperature, but when we heat it, our compound is soluble in the room temperature and the impurities are released. And then we allow it to slowly cool back to room temperature. Since it's insoluble in this solvent at room temperature, it's going to form crystals, and that will leave out the impurities in the solvent, and we can collect this by filtration. You will remember that we discussed two terms, crystallization versus precipitation. So what we're doing here is crystallization. We allow slow cooling that gives time for these crystals to selectively choose their own kind out of the solution and form a pure sample of crystals. Versus in precipitation, we quickly cool it, so it's a fast process, and these compounds don't have sufficient time to selectively choose their own kind. So if we followed precipitation, the impurities will get trapped within the crystal again. So please look at the difference between crystallization versus precipitation. Now, most often the questions that come from the recrystallization lab is you will be given some data. For example, choose whether hexane or ethanol is the better recrystallization solvent for naphthalene, and you're given the literature value for the melting point of naphthalene, and then you're given some data that was obtained using either ethanol as the recrystallization solvent or else hexane. And you're supposed to look at this data and choose which one is the better solvent, recrystallization solvent for naphthalene. As you can see, there was more recovery when we used ethanol, and the melting point was very close to the literature value. Versus in hexane, we had less recovery and the melting point range was lower than the literature value, and the range was broad. So that indicates that this sample of naphthalene is still impure. So you should be able to look at such data and then determine which solvent is the better recrystallization solvent. And we know that naphthalene is a nonpolar compound and hexane is a nonpolar solvent, so they would easily mix with each other. So that scenario is similar to this curve C here. It's soluble even at room temperature in this solvent because they have similar polar properties. Versus ethanol, it's an intermediate polar solvent. It has CH2, CH3 carbon chain and also OH group as the polar group. So it's not as favorable to solubilize naphthalene compared like in hexane at room temperature, but it's more accommodating when we heat ethanol and then it becomes more soluble. So you can use that kind of hints to help you determine your final answer. The main take-home message in the melting point lab was that a pure solid, if our sample is a pure compound, then it would melt within the temperature range that is very close to the reported literature value, and the melting point range would be very narrow. We consider a range within 0.5 Celsius to 2 Celsius as acceptable when we compare it with its literature value. And the main reason is for a pure solid to have a higher melting point is because to break these intermolecular forces, we need to provide heat. So whenever we have a pure solid, they're interacting with their own kind, so they are able to form strong intermolecular interactions. That means we should provide more energy in terms of heat in order to melt the solid into a liquid. But if our sample was impure, then these impurities are interfering with the strong, interfering from these molecules, forming strong intermolecular interactions. So their interactions are weak, which means we only have to provide less amount of heat to melt it from solid to liquid. So that's the sole reason the intermolecular forces are weakened. Therefore, less heat is required to break them. And because the impurity will also have its own melting point, this solid will melt across a broad range of temperatures and also because the bonds are weakened, the melting point would be lower than the reported melting point for this particular compound. Thin layer chromatography was another technique that we used to test the purity of final product samples that we obtain. So it can be used for both solid as well as liquid organic compounds, as well as these solids can be dissolved in a suitable organic solvent. For the purpose of this class, always consider the TLC plate is more polar than the solvent system. So if you're given a question and you are asked to think about how a particular compound would separate on the TLC plate, always consider the TLC plate is more polar than the solvent system. Now, the separation of the compounds applied on the TLC plate is going to be based on whether it can interact strongly with the stationary phase or TLC plate material, or whether it can form stronger interactions with the solvent system, which is the mobile phase. So if the interactions between the compound and the stationary phase is stronger, its movement on the plate is going to be delayed. So those kind of compounds will not move that far from the start line. And what we can say about those compounds is we can predict that those compounds have polar properties, and that is why they were able to strongly interact with the polar TLC plate, which delayed their movement on the plate. But if the compound is not polar, if it's non-polar, then it would prefer to interact more with the solvent system than with the polar TLC plate, which means it's able to move further along the TLC plate along with the mobile phase. So this is the core concept of this technique, and if you're given questions and asked to identify certain compounds in a given TLC image, then you should think about the polarity of those compounds in order to identify which spot relates to the compound that you are being asked about. Now, you might get questions where you have to calculate the RF value, which stands for retardation factor. So that is calculated by measuring the CF and SF. CF is the compound front. How far did the compound spot travel from the start line? Solvent front is how the distance between the starting line and the stop line, because the solvent is going to move all the way to the stop line. RF value is calculated by CF over SF. Now, can the RF value be greater than 1? If we think about it, the maximum distance a compound can travel is up to the stop line. So the maximum distance it can go is from start to stop line, which is the same distance as the solvent front. So if that was the case, then CF divided by SF will give 1. And since we are stopping the solvent front at the stop line, we will not get a RF value greater than 1. Let's discuss about some technical issues we need to watch out when we do TLC experiments. First of all, we should only use a pencil to draw these stop and start lines because it's made out of graphite and it will not react with the organic solvents in the mobile phase. But if we use a pen to draw these lines, the ink in the pen are also a composition of organic compounds, and they will mix with the organic solvents used in the mobile phase. So they would diffuse across the plane and interfere with our experiment. One problem we would see is spots overlapping each other. That would happen if we spot these compounds too close to each other. And these compounds diffuse a little bit as they move across the TLC plate. So if they're spotted too close to each other, the diffuse spots will overlap, making it difficult to identify the spots independently. Another problem is smearing of compound spots as they get separated. The reason for this is the amount of compound applied here in the spot is too concentrated. So there's too much material which causes it to smear across the TLC plate. The solution is to either spot fewer times, or else the best option would be to dilute your sample solution. That will help rectify this mistake of smearing. Another problem we might see is no separation between the compound spots. So if we were just trying to identify these three unknown compounds with some reference RF values, we are not able to distinguish them from each other because they didn't move far from the start line. They're all crowded near the start line. What would be the reason? We know the TLC plate is very polar. So if the compounds didn't move that far from the start line, that means these compounds must also have some polar characteristics which made them interact more with the TLC plate than the solvent system. So this also tells us something about the solvent system, that it's not very polar. So the solvent system is a much non-polar solvent system that doesn't help us to separate these compounds and move them further across the plate. However, the solution is not to make the solvent system extremely polar either. If we do that, then all the compounds would crowd at the end line. So the solvent system being too nonpolar or too polar are both a problem. So we should maintain a moderate polarity in our solvent systems. So if this was the case, we need to increase the polarity of the solvent system. If this was the case, we need to decrease the polarity of the solvent system a little bit. Let's take a look at how the same compounds would separate on a TLC plate when we change the solvent systems. We're going to consider the pink and orange spots as they are from polar compounds, and the blue spot is a non-polar compound. If we spot these three compounds in a TLC plate and use the solvent system of 10% ethyl acetate and 90% hexane, this solvent system is mainly non-polar. So this means the polar compounds wouldn't move that far, and the non-polar compound will move further with the solvent system. However, now we can see that there is not much separation between these two polar compounds. And someone asks you, how would you take care of this? How would you improve this result? Now, this was actually a post-lab question where you were asked, what would happen if you change the solvent system into 90% ethyl acetate and 10% hexane. In this case, the solvent system is extremely polar because we have 90% ethyl acetate, so very polar solvent system. A lot of you thought that this would cause the polar compounds to move all the way up to the stop line, while the nonpolar compound would not move at all. So this assessment is incorrect. What happens is all three compounds will move up to the stop line. So the reason is, obviously for the polar compounds, now the solvent system is very polar, so they are able to form more favorable interactions with the solvent system and they will move all the way to the top. But for the nonpolar compound, it doesn't really have a choice. It doesn't like the polar TLC plate and it doesn't like the polar solvent system either. So it's only going to move via capillary action in like a way to get away from these the TLC plate and the solvent system. So it's going to move all the way to the top either way. So we should never make these kind of drastic changes. If we wanted to improve this result, we should try increasing the polarity of the solvent system by a small percentage, like from 10% to 15%. And that would help us to separate the two polar compounds from each other. And that would be more helpful in order to identify them compared to changing the solvent system very drastic manner. The last technique that we learned about in this class was extraction, which is another technique we can use to purify organic samples from mixtures. And in this technique, we try to manipulate the solubility of organic compounds in the mixture to separate them between two immiscible solvent pairs. So what we're trying to do is make one of the compounds soluble in the organic layer and change the other compound in the mixture so it becomes soluble in the aqueous layer. And then by separating the two liquid layers, we are able to separate the two compounds from the mixture. Which layer is going to be in the bottom or the top is going to be dependent on their density. If the organic layer has a lower density compared to water, it will be on the top. If the organic layer has a higher density than water, then the organic layer will be in the bottom. Now, an organic solvent that is suitable for extraction should have these properties. It should be immiscible with aqueous solutions. It should have a wide solubility range for many different organic compounds. It should have a low boiling point, and it should not have any chemical reactions with the compounds we are trying to isolate. Often in the exam, the questions that come related to extraction is, what steps would you follow if you had to separate a mixture of a neutral compound with an organic acid or a neutral compound with an organic base? So we're going to look at some examples of organic acids. So we can have carboxylic acids. There can be sulfonic acids, phenols, enols, alcohols, or thiols. So the common characteristic in all these compounds are they are weak acids and they have a hydrogen that they can give away if they are mixed with a base. So once these compounds are deprotonated, they become ionic compounds and they would become water soluble, allowing us to separate it from the other compound in the mixture. Now, organic bases are normally compounds that contain nitrogen. So those would be compounds with either primary, secondary, or tertiary amines, amides, or imidazole type molecules. I'm not sure if I'm drawing this properly, but probably something like this. So the nitrogen has lone pairs, so it would be able to take up a proton. So each of these compounds, the nitrogen has a lone pair which it can use to accept a proton from an acid. And in the process, it will acquire a charge which makes the compound an ionic compound and more water soluble, so we can separate it from the other compound which is soluble in the organic layer. Now here are two examples for each of those scenarios I mentioned in the previous slide. The neutral compound is naphthalene mixed with benzoic acid. How to separate this kind of mixture using extraction? First of all, we will have to dissolve both of these in a common organic solvent. As they're not water soluble, and we can't really make naphthalene water soluble because it doesn't really have any functional groups that we can use to manipulate it. However, you can see that benzoic acid has this carboxylic group which we can manipulate in order to make it more water soluble. Since it's an acid, we're going to add a base and they will react and convert benzoic acid into an ionic molecule. Now it's soluble in water, and we know that ionic interactions are the strongest type of intermolecular interactions, and ions can form ion dipole interactions with water molecules. So although it wasn't water soluble in its first form, now its ionic form, the ionic interactions are strong enough to carry the bulky aromatic ring into the aqueous layer. However, we want to so at this point we are going to have an aqueous layer and an organic layer, and since naphthalene is neutral and it's not water soluble, it's going to remain in the organic layer. And by separating the two liquid layers, now we have separated them from each other. And the next few steps are all about isolating the compound out of these solutions. We're going to convert the sodium benzoate back to benzoic acid, and for that purpose we are going to add a stronger, more concentrated acid like 6 molar HCl. Why do we use a more concentrated acid is because there could be extra base left in the aqueous layer, so we need enough acid to neutralize that and also protonate the sodium benzoate. So once it turns into benzoic acid, it's no longer soluble in the aqueous solution, so it's going to precipitate and we can collect it by filtration. Over here, to obtain the naphthalene, first of all, we do some drying steps to remove any traces of water from the organic layer. And we can do that by washing the organic layer with saturated sodium chloride, or we can mix the organic layer with some anhydrous sodium sulfate. Both of these are ways that we can draw out traces of water left in the organic layer. And next, we can evaporate the organic solvent. This is why we want an organic solvent with a low boiling point, so it would quickly evaporate before reaching high temperatures, which could disintegrate our compound of interest. So once the organic solvent is all evaporated, we will have isolated naphthalene. Now on this side, we have naphthalene versus an organic base. And you can see we start off with the same step. We dissolve the mixture in a common organic solvent. Since this is an amine, it's a base, so we are going to add an acid in order to convert it to an ionic molecule. And we will have an aqueous layer and organic layer, which we can separate. Now the two compounds are separated from each other. The rest of the steps are all about isolating them. This is now a charged molecule because it's gained a proton, so it can form ion dipole interactions with water molecules and become water soluble despite having a bulky aromatic group. To get back the base, we are going to add 6 molar sodium hydroxide. Again, the higher concentration is to neutralize any excess acid left from this step and to deprotonate this NH3 plus group. Once it loses its charge, it's going to precipitate in the aqueous solution, and we can filter it in order to isolate the amine. On this side, for isolating naphthalene, you can see the steps are exactly the same as we followed in the previous example. So you can see that there is not much difference in these steps. You only have to remember a few things, but the only difference is you have to identify which molecule, one of the molecules in the mixture, whether it's an organic base or organic acid, so you know which reagent to add in this second step and which reagent to add in this third step. We learned about the synthesis of 1-bromobutane via an SN2 reaction where we started off with 1-butanol. So I'm not going to explain these reactions. These are the 3 reactions concerning the experiment that we did for SN2 lab. So please go over them and follow how the reaction mechanism occurred. What I'm going to discuss is this post-lab question asked in that lab report that was to give a method which we could use to successfully separate 1-bromobutane from 1-butanol, because in the crude product mixture we had the product 1-bromobutane, but we also had some leftover 1-butanol. So if you go back to look at the lecture slides for this lab, you would see that there are 3 slides discussing possible options to isolate 1-bromobutane from the crude product mixture. One of them was to wash the product mixture with sodium hydroxide. So we know sodium hydroxide is a base, and we know that this OH group can behave as a weak acid. So you would expect this hydrogen to be taken up by the base and the oxygen to become deprotonated and a charged molecule. So now this charged molecule will become water soluble. However, the NaOH will also react with the bromobutane. It will induce an E2 elimination reaction, and this bromobutane will be converted into an alkene. So we can't use NaOH in order to separate them. The second option was maybe, well, we tried a base, so maybe we can try adding HCl. So if we add HCl, we could convert the butanol, the OH group, into an oxonium ion, like what happened in the actual reaction, where it was instead of HCl, what we had was HBr. But again, we come across a problem because so when we have the chloride ion, it's going to serve as a nucleophile, and since this OH2 plus is a good leaving group, it will leave in the presence of this strong nucleophile, and we're going to end up with 1-chlorobutane, and that cannot be distinguished from 1-bromobutane, so we cannot use HCl either. However, adding sulfuric was a much better option because it would convert the OH group into an oxonium ion, and once the sulfuric has lost one of its hydrogens, what there will be left is this bisulfate ion, and it's a very weak base, so it's a weak nucleophile, and it will also not react with 1-bromobutane, and it's not going to cause this OH2 plus to leave, so the butanol is going to be remaining in this charged state, therefore it can become water soluble. So if we do an extraction using sulfuric acid, we would be able to successfully separate 1-butanol from 1-bromobutane. Next, we learned about the Diels-Alder reaction, which is a mechanism we can use in order to prepare cyclic compounds. And this is mainly a reaction between a compound that we call diene and another compound called dienophile. Dienes are 4-5 electron systems, which means there are 2 double bonds, and dienophile is a molecule where a double bond is in close proximity to an electron withdrawing group. Since electrons are withdrawn from this double bond, it's kind of lacking in electron density. So if we mix it with a diene, it's going to cause a nucleophilic attack from this carbon, where the electrons will flow this way, and that will cause a cyclic reaction, and you can see the new bonds will form between this carbon and this one, and another new bond over here. So these two are the new bonds. This part came from the diene, and this part came from the dienophile. And it's easy to identify, like if you were given the product and asked to predict or figure out which were the substrates that prepared this molecule, you have to start with a place where there's a double bond. So that means in its substrate, there used to be a double bond over here and over here. And then the bonds right next to where those previous double bonds existed, those are the new bonds. So they were newly formed bonds. And then we have the rest of the molecule. And since here are where the new bonds form, that means the double bond must have existed here, and that is it's next to this electron withdrawing group, so it makes sense. That way you can identify the starting materials. So this could be a question in the exam where you are either given the product and asked to choose which ones are the correct substrates, or you are given some substrates and asked to figure out which one is the correct product of the Diels-Alder reaction. Finally, we did the E1 and E2 reactions lab. So let's take a look at each mechanism, and the importance is to understand the differences between the two mechanisms. Let's first look at E1 mechanism. So E stands for elimination and 1 means it's a unimolecular reaction. However, it happens in 2 steps. So it's unimolecular, 2-step reaction, and the rate of this reaction depends on rate constant times substrate concentration. Now, first of all, these 2 steps are where we see the E1 reaction happening. The first reaction is about converting this OH group into a beta-leaving group. So the first step in E1, the leaving group leaves, taking the electrons it was sharing with this carbon, and that causes the molecule to form a carbocation. And in the next step, the carbocation tries to take away its positive charge by attracting electrons. One of these protons are sharing with this carbon, and that converts the bond between these 2 carbons or these 2 carbons into a double bond, and we end up with an alkene. And the proton that's lost is going to be accepted by this bisulfate ion, which was produced during this first step where we were converting OH into a beta-leaving group. So the main points is in E1 reaction, the nucleophile is a weak nucleophile. It's a weak base, and stereochemistry doesn't matter much in E1 reaction because it forms a carbocation, and stereochemistry doesn't play a role in whether a hydrogen is lost from this carbon or a hydrogen is lost from this other carbon. Therefore, stereochemistry is not really important in this reaction. Now we learned about the Zaitsev rule, which means always these reactions occur in a way that they produce molecules that are most substituted. So we could see that these two butene both have two substituents, and one butene only has this one substituent. So we don't count the hydrogens as substituents. So 2-butene has two substituents adjacent to the double bond, but 1-butene only has one substituent. The more substituents there are, there is more ways the electrons can spread around the molecule. That means more resonance structures. That means those molecules are more stable. So in the Iwan reaction, the Zaitsev products are going to be 2-butene, trans and cis, and from those two, trans is going to be the major product because it has less steric hindrance. And 1-butene, the minor product, we call it as the Hofmann product. It's not going to be favored that much, so there will be very little amount of Hofmann product forming. Now, if we will go to the E2 mechanism, E is for elimination. 2 means it's a bimolecular reaction. So 2 molecules, it's bimolecular, a one-step reaction. And since it's a bimolecular reaction, the rate depends on both the substrate concentration and the nucleophile concentration. Since this is a one-step reaction, that means the nucleophile accepting one of the protons that is lost and the leaving group leaving, it all happens simultaneously. And the most efficient conformation for the leaving group to leave and the proton to be lost, the leaving group and the proton that is lost should be arranged in an anti-periplanar position. That is, they should be 180 degrees. They should have a 180-degree difference in their arrangement in the spatial configuration. So because they have to be in that specific configuration, stereochemistry is important for the E2 mechanism. And because stereochemistry is important, which happens in the transition state, the formation of 1-butene is favored a little more compared to E1 because 1-butene transition state is more stable than the transition state that forms cis-2-butene. So overall, E2 mechanism will also follow Zaitsev rule and produce more of the Zaitsev products, but compared to E1, it will form more Hofmann products. And we need to have a strong base, a strong nucleophile, and a bulky nucleophile in order to avoid it favoring an SN2 reaction. So if it's bulky, it can't approach these carbons as easily, so it will not undergo a nucleophilic attack. It will mainly just end up accepting these hydrogens that is lost. So it follows the E2 mechanism. This slide, I summarized the differences between E1 and E2. So take a look at it and see the differences. So those would be helpful in answering questions related to the E1, E2 lab. Finally, I want to remind you guys about the calculation of theoretical yield. So it's always going to be dependent on the stoichiometry in the reaction. So this reaction is the Diels-Alder reaction, and we can see that 1 mole of 1,3-butadiene if it reacts with 1 mole of malic anhydride, it should produce 1 mole of this product because their stoichiometry is 1 to 1 to 1. So if you are given the amount weighed for, say, malic anhydride and 3-sulfolane, because we couldn't directly measure 1,3-butadiene because it is a gas. So instead of measuring a gas, we measured 3-sulfolane and obtained the 1,3-butadiene gas, reacted it with malic anhydride. So if you are given the amounts that were weighed and the molecular weights of those substrates, you should figure out how many moles were weighed for each of these. So since this is also a 1 to 1 reaction, 3-sulfolane breaking down to 1,3-butadiene, so if you had an X number of moles of 3-sulfolane, you would get X number of moles, the same amount for 1,3-butadiene. We assume that the reaction is 100% performing 100% efficiently, so we expect the same amount of molecules to form for 1,3-butadiene. And you should be able to calculate the number of moles of malic anhydride. Compare the two numbers, compare the numbers in moles, and whatever is the smaller number, that reagent would serve as the limiting reagent. And that is because this is a 1 to 1 reaction. If it was a different reaction where the stoichiometric ratio is different, then you would have an extra calculation, which you don't have to worry about for this class. And in order to get the theoretical yield, once you identify the limiting reagent, let's say malic anhydride was the limiting reagent, and there was a Y number of moles of malic anhydride. Since the stoichiometric ratio is 1 to 1 between malic anhydride and the product, theoretically we can expect Y number of moles to form. And in order to get the theoretical yield, we multiply that number of moles from the molecular weight of the product. So remember, the theoretical yield describes how much of the final product we can theoretically obtain based on the amount of each reagent we used. So we have to multiply the number of moles by the molecular weight of the product, and then you can obtain the percent yield. So practice calculating the theoretical yield. That could be a question where you have to calculate and enter the answer as a number.